So, Stacy, do you hear me? I think that if you tap on the headset sign, then your microphone will be active. So our next speaker is Stacy McGaugh from Case Western Reserve University. And the title of the talk is Regularity in the Dynamics of Rotating Galaxies. So Stacy, please, you can start your talk. Could you please tap on the microphone sign?
Can you hear me now?
Yeah, we can hear you. Please start your talk.
Very good. Thank you for having me. It's a wonderful, if somewhat strange experience to be communicating in this way. I apologize for speaking in English, but I think your English is much better than my Farsi. So,
thank you, Stacy. Excuse me, may I interrupt you?
Of course.
Could you please turn on your webcam? If it causes some problems, then I will ask you again to turn it off.
Okay. I did lose my connection at one point during Benoit's talk, so we'll have to do that. Hopefully this will be okay. So
we see you
it
now.
appears that, okay, very good. So hello, welcome. Again, thank you for having me. I want to basically tell you things related to what Benoit just told you, but largely from an empirical perspective. I think before we can agree on an interpretation of what's going on in our universe, we have to agree what we see in the data. And so I'm going to emphasize largely the empirical aspects, things that I think are true. And there was already a question about, okay, some deviations from Tully-Fisher and so forth. So this is my perspective on what I think we need to. I want to acknowledge my collaborators, Jim Schomburg at the University of Oregon, who has worked on the surface photometry of galaxies and has been a collaborator of mine for many years. Federico Lelli, who was a postdoc at Case Western, has moved on to Cardiff and is really responsible for building the Spark database that I will be talking about. And then also Pingfei Li, who is currently a grad student and about to defend any day now. So he should be defending his month. Okay, so this is sort of my quick summary of the things that I think are true in the data that any viable theory has to explain. So strictly speaking, I'm just going to talk about galaxies that rotate, spirals and irregulars. As near as I can tell, these apply to pressure supported systems as well, but I'm not going to take the time to dive into those. So strictly speaking, just about rotating galaxies. And of course, these are famously observed to have flat rotation curves emerging from the 70s and the early 80s, as Benoit reviewed. And a lot of our current ideas were launched by that revelation, but they were not informed so much by these other things, which I think are also true. Renzo's rule, which is coupling between or at least a correspondence between features in the light profile that are also seen in the kinematics of the rotation curves, baryonic Tully-Fisher relation, as Benoit mentioned, what I call the central density relation, and I'll describe that more, and of course the radial acceleration relation, which sort of ties all these things together, but it's useful to think of them each distinctively. So all that I say here is going to be based on the Spark database that Federico Lelli built while he was at Case. And basically what we did was to collect all of the galaxies with 21 centimeter data cubes that we could put our hands on. That's a very expensive observation to make. So 176 galaxies with full cubes from radio interferometry is really a huge data set. People who work with Sloan think, oh, well, 10,000 galaxies, that's a large number. But they don't have the H1 data in the same level of detail. So for these kind of data, that's really critical. You need to know where the gas is as well as where the stars are. And so it's really a huge sample by that standards. Now, what we did ourselves is to measure the stellar distribution using the Spitzer Space Telescope. And so the Spark teams ourselves, Federico, James Schaumbert, and myself, we have uniformly analyzed the surface photometry of every galaxy that's in the database. So that's really our contribution to this side of it, is the photometry side. The other side of it is all of these rotation curves that I alluded to. Those we have collected from the literature, and we'll go ahead one slide. This is really the integrated work of an entire community of radio astronomers. Both Federico and I have contributed to some of this work, and so I feel comfortable that we have a reasonable understanding of the data. But we ourselves did not collect the rotation curves, so that's a separate piece. What we did do is a surface photometry, and what we're really wanting to do is use the light distribution to map out the stellar mass. I don't feel like I have time to go into the details of the stellar population models, so I will just summarize by saying that the best, in my opinion, the best mapping of what you see in the starlight to what you want to know in terms of the stellar mass for the physics is provided in the near infrared, either the K-band at 2 microns or the Spitzer 3.6 microns. The scatter in the mass to light ratio is minimized there, as is the sensitivity to the star formation history of each individual galaxy. That still introduces some scatter from galaxy to galaxy, so the mass to light ratio is not exactly the same, of course, but to a surprisingly good approximation, it is close to that. So what we would adopt throughout this talk is a simple model in which the disks of all galaxies are assumed to have a mass to light ratio in the 3.6 micron band of 1/2 in solar units. That corresponds to about 1.4 in the optical V band, and slightly higher for the bulge components, about 0.7, because they do have a different star formation history, though that is a small minority of galaxies where we have to do that. And one thing I like about this is that even though it's not right in detail, there's also no way to really say ahead of time, oh, this galaxy has slightly higher mass to light ratio than that. It's all lost in the scatter. And so we're just using this as a scale to relate what we observe directly in the starlight to what we think is there in the stellar mass. So there's no fudging, it's just what you see is what you get. And this is just a necessary constant to do that. Okay, so we'll assume that throughout. The Spark database has the mass distribution of both stars and gas in the H1 line. So this is the atomic gas map from the data cube for this particular galaxy. This is an infrared image of this galaxy, and they are to the same physical scale. So the atomic gas really is more radially extended. That's a very common feature of galaxies. There is more stellar mass in this case in the stars here, so the mass is more concentrated. But in order to talk about the sort of things that I think are important here, you need to have both. And that's why you really need to have the H1 data cube as well as the atomic gas mass, as well as the infrared map of the stellar mass. Okay, so just a sort of a broad overview of the sample and what it shows you in terms of physical properties. I have plotted here against the stellar mass, both the gas mass and the size is measured by the scale length of an exponential disk fit. So note there's a huge range of stellar masses present from a few times 10 to the 11 down to below 10 to the 7th solar masses. A lot of samples in the literature only give you this higher mass end. And you can see that in the gray points over here, which are drawn from an optical sample. There is the raw counts from Sloan in that grayscale there, and you can see how it peaks around L star basically, and then it falls off very steeply. And that, of course, is just a selection effect. These galaxies are faint, they're hard to see, and so you do not see them as far away in the universe. And so this edge is just the volume sampling effect that happens. You see brights far away and faint ones only when they're up close. But as you remember from the stellar mass function that Benoit showed, of course, there's plenty of galaxies at these masses intrinsically per unit volume in the universe. So you want to sample that. And so Spark does a very good job of sampling this full range and not concentrating on this bright end. And things do change here. So this is a line of constant surface brightness cutting across this. And so these galaxies are higher surface brightness. These galaxies are lower surface brightness. That is, their stars are more spread out. That surface density is a really critical thing, as we'll see. When you get to lower mass galaxies for the field, they tend to be gas rich. So this is the one-to-one line, bright spirals like the Milky Way, which is sitting right there. Those tend to be star dominated, you know, maybe 20% gas. When you get to lower mass galaxies, they're actually more gas than stars. So again, you really need to know about both. And if you're just looking at the stars here, then you're only seeing a third of the picture. So one of the benefits of the 21 centimeter data cubes is that in addition to giving us a map of the gas distribution, they also give us these sort of beautiful velocity fields. So this is the same galaxy I showed you before. And one can derive the rotation curve by fitting in rings this equation to find out what the circular velocity is. And that varies in azimuth, being maximized along the kinematic major axis, but you have that full spatial information so that you can actually fit a sinusoid around the ring and find the best fit values of the circular velocity. If there's any non-circular velocity, though in practice it's very hard to perceive that, and what the inclination is. So all of the galaxies in the Spark sample have some kind of data like this. Not all of them this beautiful, and so it does take some human judgment to decide what to trust. And as always in astronomy, that is a matter of judgment. You cannot always rely on the stated error bars. There's all sorts of technical reasons. I have seen people take our data, which is all available on the website, which you can get off of this PDF, and do things with it, treating the data as a black box, treating some Bayesian analysis code as a black box. And if you put a black box in a black box, you will get an answer that you don't understand. So I do encourage caution in interpreting everything, which is why I am trying to emphasize what I think is empirically true here. So of course, rotation curves are flat. This is a figure from one of Vera Rubin's papers in the late 70s. I don't think I need to rub this in, though I do want to note that at this point, this is a de facto law of nature. We tend to be shy about using those words, but every time we see a galaxy, this is what we observe. So that really is a sort of a Kepler's law for galaxies. The rotation curves become flat as you get far enough out. And we have not yet seen any indication that that changes far enough out. There are hints in a statistical sense, but no rotation curve is clearly observed to decline, no matter how far out we've been able to trace it. So these are the rotation curves in the spark sample, color-coded by surface brightness of the galaxies. That surface brightness, how spread out the stars are, is a really critical feature, and you can see almost perfect rainbow spectrum here. Surface brightness galaxies that have slow rising rotation curves that only slowly roll over, to high surface brightness galaxies that shoot right up and flatten out, or even decline a little bit before they flatten out. So you can see a lot of systematics already just by eye in this figure. Tolley-Fisher is this flat level of velocity corresponds with mass. These galaxies are lower mass, these are higher mass. Central density relation is this diversity that you heard Benoit talking about. And you can see by eye the importance of the surface brightness. It gives you that perfect rainbow color. And this is one of the things that's really satisfying to me. I noticed this a long time ago using optical data, but the colors were mixed up because of the scatter in the mass to light ratio that you get in the optical bands. Once we got all of this data in the near infrared, then that scatter almost disappears and you just get this perfect rainbow, which is a very satisfying result to me personally, having worked on this a long time. And that was, of course, the point of going to the near infrared, was to get that better mapping of stellar surface density. Now, once you have that, so here's one of the near infrared images of low surface brightness galaxy. Here's the surface photometry. So surface brightness is a function of radius, azimuthally averaged in rings. That blue line is a fit to the exponential disk. So the slope there basically tells you that scale length. I plotted it a few slides ago. But there are also features like this. You want to call that a bulge or a star pile. I don't care. It's a real feature in the light distribution. And so we do not use these exponential fits in the dynamics. What we do is solve the Poisson equation numerically for the observed surface brightness distribution, assuming that fixed mass to light ratio that we talked about. So basically, you can predict what the radial acceleration of a test particle in the gravitational potential of this stellar disk should be by this way. So basically, we're just asking, if only we had the stars, if only we had the gas, let's put a test particle in that gravitational potential and predict from Newton's equations, the Poisson equation, how that particle would orbit. And so we get what I call G bar there. That is the acceleration that is predicted, the centripetal acceleration that is predicted for the baryonic gravitational component. And this allows us to build a what the mass model, which is what the rotation curve should be in the absence of dark matter or MOND or whatever funny business is going on in the universe. And so this solid line here is the rotation curve corresponding to that baryonic centripetal acceleration. This is what Newton predicts for the observed distribution of stars and gas. And so there are three components here. There's the gas, there's the stellar disk, which is dominant in this case, and there's also this bulge. And notice this bulge, there's a tiny little bulge there. It's only about 6% of the total light, but it's also very compact. V squared goes to m over r, so m is small, but r is also small, and so it does have a noticeable impact on the total rotation curve. Obviously, these fall short to explain the total observed rotation, hence the mass discrepancy problem. That's what this difference is. Now, we can do that for all the galaxies in the SPARC database, and that is provided on the SPARC web page, and you can download those data and play with them to your heart's content. We have mass models for the disk, the bulge, the gas, and so forth. But this brings me to what I call Renzo's rule. This is well known to practitioners of rotation curves, but doesn't seem to be well known outside of that rather specialized circle. Renzo Sanchisi basically summarized his brilliant career in one sentence, that when you see a feature in the light, you see a corresponding feature in the rotation curve, and vice versa. So here are two examples. This is the galaxy I just showed, and that bulge, that tiny little central concentration of light, is such a feature in the light, it predicts that there should be a corresponding feature in the rotation curve, and there is. And Renzo both, starting in the mid-90s, is that this is also true in low surface brightness galaxies. So in the bulge components of most galaxies, those are very high surface brightness, and basically the stars are all the mass that matters there, and so this is just well, duh, Newton predicts it. You have that much stellar mass, you have to have that rotation curve. In low surface brightness galaxies, typically the baryonic component is far below the actual rotation curve. And so you would expect these things
Stacy, do you hear me? We do not hear you. No, we do not hear you. Could you please log out and then log in again? Oh. Stacy, we do not hear you, and also we do not see your video. Can you please turn on your microphone?
Hello, I hope I'm back now.
Yeah, we hear you.
Okay, sorry about that.
Thank you.
My fault, or at least the connection on my end just mysteriously dropped.
I don't mind it.
So sorry
Thank
about that. As I was saying, there is a feature predicted in this particular galaxy that you would not expect to be imprinted on the rotation curve if the reason for this high rotation curve is a dynamically hot dark matter halo. This just is not enough to have an impact on that. And yet, you do see a correspondence between those features. Renzo actually first said this to me in the mid-90s. He didn't publish it until a decade later because he spent that time agonizing over whether this was true in low surface galaxies. And as best we could both tell, it is. So that is the thing that needs to be explained that I think is widely appreciated. There's a really good correspondence between features that are predicted in the rotation curve and those that are observed there, even when the discrepancy is large. So then there's the Tully-Fisher relation. Massive galaxies rotate fast, low mass galaxies rotate slow. So you have all these rotation curves that flatten out. And it really does appear to me to be the amplitude of flat velocity that matters. So one can use line widths or Vmax or some other proxy. And I won't take the time to go into that. Benoit alluded to this as well. It's really the flat velocity that matters to this. So I'm just going to use that here. And that is a very strong correlation between mass, and again, you can use different proxies for the mass, the luminosity, the stellar mass, or the total baryonic mass. And that's what's shown here. So on the left is stellar mass is plotted against V flat. Milky Way's location is shown up there. Over here, we have the baryonic mass against V flat. And by that, I just mean the sum of stellar mass and gas mass. And you can see as you go to lower mass, these galaxies are more gas than stars. So it appears like the relation is bending, but it's just an artifact of not accounting for the mass that we know is there. And so you add that gas mass back in and you get this smooth power law over about 5x in mass. And it's very steep, approximately a slope of 4, as Benoit said. Notice also that thank you. The scatter goes up as you include lower quality data. So the gray and the blue points are just basically whether you have a good distance or not. And when you have good data, the scatter goes away. And I think that's the answer to the question that was posed earlier. For the super spirals, most of them live up here. Some of them live over to the right. None of those would pass the quality criteria that I've imposed here. And looking at those data, they don't actually show the rotation curve, but it looks to me like they've only measured at 2 or 3 scale lengths, whereas a rotation curve like that won't flatten out until you get to much larger radii, and it has a classic shape that peaks and then falls. So basically, they're just seeing that peak V max rather than V flat. So I do not think there is any serious evidence for deviations from this Tully-Fisher relation when you measure V flat and the baryonic mass, and you have to do both of those things, otherwise you get a different relation. This line is a line of slope 4. It's not a fit other than the normalization. It is adequate, and this gives you this really handy. You know one or the other, you can estimate the other in your head pretty much. But this line of slope 4 corresponds to a line of constant acceleration. All galaxies sort of fall on that line. So I lost a fair amount of time to that internet glitch, so I'll move along a little bit. Tully-Fisher is out here. In the interior region, there is also a relation that we call the central density relation. And basically, if you work out what the dynamical surface density is from the rotation curve, and compare that to the central surface brightness in stars, then again, there is a relation at high surface brightness. That's just a one-to-one relation where stars dominate and Newton suffices. But the relation persists for low surface brightness galaxies where there is a mass discrepancy. If there was none, everything would be down here on this line. And yet, it's not just a hodgepodge of things. There's a very strong relation. And so you can predict the diversity of rotation curves by just reading off the central surface brightness. That is, the surface brightness you see is predictive of the dynamics that you get. Where this bend in the relation occurs at a particular surface density, multiply that by Newton's constant, and it's also an acceleration scale very close to the one that was indicated by Tully-Fisher. And you can do the same thing with the entire rotation curves, the radial acceleration relation. I'll skip over some of the pedagogical pieces here. And just to note that this is G bar, this blue rotation curve, that's what the baryons predict. This is G off, what you actually see. And if you plot the rotation curve, then you don't see any systematic. If you plot acceleration, that is the observed acceleration against that predicted what you see, then everything falls on the same line that we call the radial acceleration relation. And everything else that I've mentioned can be derived from this. Flat rotation curves occur because of the asymptotic slope here. You cannot have a different relation and also have flat rotation curves. It's got to have that asymptotic slope. At high surface brightness, there is no need for dark matter. The amount of dark matter or whatever becomes systematically greater once you get below a critical acceleration scale, and it increases systematically with that lower acceleration. You can fit a line. The only free parameter there is that acceleration scale. And once again, it comes out to about the same number of 1 angstrom per second per second. It's just a tiny, ridiculous number. But that's what galaxies work at. And you can say, okay, well, here we just fixed the mass to light ratio and all the points more or less fall on top of each other. They do not exactly do so. So you can fit for the mass to light ratio, that is, ask what mass to light ratio is required to put things as well as possible on the mean radial acceleration relation. And you can do that for all these different galaxies individually. So we have the rotation curve fit in the plane, the radial acceleration radius, and the fit parameters. And this works remarkably well. And you can do this a whole bunch of times. Now the slide advance is going to be slow. So I'm just going to skip through these. Now, if you look closely at these things, you will find cases that do not fit. That is the nature of astronomy. There's always some weird cases. However, they are a distinct minority. The vast majority of these things work really well. And so I'm more concerned with explaining that first than worrying about a few outlying trees. And there may be outliers, and if those are real, then that's an important thing. As near as I can tell, the outliers are not real. They're just the expected scatter. The astronomical data are never perfect. So we can put all that together in a residual diagram, which has yet to come up for me. And what you'll see is two versions of that. One, just the residuals from the predicted rotation curves, assuming a flat, constant mass to light ratio. And another, the residual diagram with the best fit mass to light ratios. And I'm sort of stuck here. So is anybody else seeing the slide, or is it just blank?
We see the file now. Stacy, I just want to say that your time is over. Sorry.
Okay. There were, oh, here's the slide finally. Basically, there's some scatter. It either is in the rotation curves or in the mass to light ratio, and of course there should be some scatter. So let me just summarize. All these systematics are tied together by a characteristic acceleration scale. Those could be logically distinct, but they're all the same number to within the accuracy. And so my opinion is that we need to understand these five essential things. It's not just that rotation curves flat, but that you also have these other systematics, and that they're all tied together by this characteristic acceleration scale in the data. So thank you for paying attention and for putting up with the internet problems, and I'm happy to take questions.
Thank you so much, Stacy, for your informative talk. Any question, comment? Any question? Hossein Shanavar, please ask your question.
Hi, thanks for your talk. My question is, in your paper related to bionic Cliff-Fisher relation, the objects with rising rotation curves, these objects are excluded. You mentioned that Rubin-Bossma law, I think. Is that related? I mean, do you exclude these objects because of that law?
Well, yes. So the empirical experience that we have had is that low surface brightness galaxies have these slowly rising rotation curves, and any given observation does not necessarily get all that far out. And so you don't see all the way out to the flat cases. So in the cases where we have been able to chase them farther out, saying, okay, this one wasn't good enough, let's go get better data, we have always seen them flatten out when we get farther out. Now, of course, we don't know in every case because we haven't been able to do that in every case. But, you know, every time we are able to chase it further out, we see that flattening. So when I mention, you know, things falling off of Tully-Fisher or not and imposing a data quality criterion, that is the quality criteria, that you have to see the flat part to 5% at least. If it's changing more than that, then we haven't really gotten out to the flat part. And so you can also find claims in the literature where, okay, there are galaxies that fall off the low mass end of Tully-Fisher, and those are almost always cases like that where they just don't chase the rotation curve far enough out. So we've treated those as don't know, basically.
Okay, thanks.
Any other question? I have a question for you, Stacy. There are some papers appearing on arXiv claiming that RAR is something emergent and not fundamental fact. What's your own view on this? Is that RAR a fundamental thing?
Well, there's a long history here, so you ask a Dane question for the time that we have. There are many claims now that this is now emerging from galaxy formation simulations. And a lot of the papers making this claim seem to treat it a new discovery as of 2016. What was new in our work of 2016 was the Spitzer data I've been telling you about. But I've been talking about the same relation going back to the late 90s. And Bob Sanders was talking about it before that. Now, if you ask the same community about those relations back then, they would say they're not real, and because they don't agree with their simulations. So the data have not really changed. They've proved. The story coming out of the galaxy simulation community is what has changed, and they have spent the last 20 years fine-tuning their models to make them look like galaxies. So it looks to them like, oh, I look at the models and plot this out. There it is. So I predicted this, and that's not at all what happened. Really, quite the opposite. So I do not doubt that one can build a simulation that does this, but it's also just true from the history of simulations that you can build simulations that not do this. And so, you know, it's not at all natural